So this is the descriptive statistics section in Econ 307, financial data modeling. So the purpose of this course, there are three main things we want to do. The first is we want to make sure we have an in-depth review of probability and statistics, more on the statistics side, some probability with distributions. We want to make sure we have adequate data skills by the end of the semester. So we'll do mostly Excel. I may show you a little bit of stuff in R, but it's mostly going to be Excel based, things that you would use in your other finance and accounting classes. For econ majors, you're going to use more R as you move forward, and I'll cover a little bit of that, but it will mostly be extra. Most of the course is going to be in Excel, getting very familiar with Excel functions, how to work with data, how to do some basic data cleaning, rearranging columns, making plots, summary statistics, and mostly just using Excel's built-in functions. And then we're going to apply the stuff that we learn to business and finance. A lot of the data we're going to work with is stock data with stock returns, or actually stock prices, and then we'll convert those to returns. And that's mostly what we're going to be working with, but we'll also work with a lot of housing data. Since I'm interested in real estate and real estate research and housing markets, I'm pretty familiar with that data, so I'll use a lot of that as well. And the course has three parts. The first is mostly going to be a review of Econ 206. If you haven't taken Econ 206, it's possible that you have AP credit for a statistics class and you didn't take Econ 206. So there are some things you may have to catch up on, because it's my understanding that a lot of the AP statistics is taught using a graphing calculator, and that's not what we're going to do in here. The business world does not run off of a graphing calculator. It's mostly using Excel, so that's what we're going to use. So I'll have plenty of videos to get you up to speed. If you're not familiar with Excel or if you've never used Excel, I teach this class with assuming zero exposure to Excel. So we should be able to get you up to speed pretty quickly. Regression modeling will take up kind of the second third of the class. So the first exam will be mostly the review and extensions of Econ 206. The second exam, mostly regression modeling. And then the last section will be financial modeling. So we start to analyze portfolios, maybe do a little bit of option pricing just to show you the basic statistics behind those models under very simplified assumptions. It's not really going to be the most realistic scenarios, but it will give you an idea of how that works. And just as a reminder that this is not a finance course. I know it's financial data modeling. It's a statistics course, and the applications are in accounting, finance, business. For those of you that are math, econ, actuarial science majors, we'll talk about some applications there as well. So just to get more into the content here, there are two types of statistical techniques that we're going to use throughout the semester. The first is descriptive statistics. So this is what we do to describe the distribution of a variable in a sample. And it's important to note that we're working with samples. We're not working with populations. So the population would be every possible observation. So for example, the student body at WKU could be the population. So that's what we're interested in. But we typically only work with a sample from that population. So we may have a sample of 50 students. We may use the class as a sample. So we're describing some variable. It could be the average age, the GPA, but we're describing that variable from the sample, not the entire population. A variable is anything that changes observation to observation. So if I have 50 students in a class and I go around the room and I ask everyone their age, that age is going to vary person to person. Now, we may have multiple people who are 21 years old. But my bet would be if you go down to the actual birth day, the hour, the minute, the second they were born, technically they're different ages, even though we typically record age in years. Age is a variable. Height, weight, GPA, all of those things are variables that we could use to describe the sample of students that we are working with. A data set is just comprised of variables. So if I have 50 students and I ask all 50 students their age, their height, their weight, their GPA, that would be the data set that I'm working with. So the data set would just be a set of variables that we want to analyze. The other type of technique is inferential statistics, and this is when we take what we learn up here from working with a sample and we try to make some inference about the population as a whole. So let's say I'm interested in the average age of students at WKU, and the sample that I have is the class that I'm currently teaching, the students enrolled in this current course. Well, if I take the average age of students in this class and I use that to infer or make inference about the average age of the population at Western, I'm not going to get a very good number. The estimate's going to be very, very poor because my sample does not reflect the population. But if we can assume the sample that we have reflects the population, that the sample, the distribution of students in the sample reflects the distribution of students in the population, then we can take what we learn from the sample and make inference about the population. It's not going to be perfect, and we'll talk about confidence intervals and different ways of constructing or estimating the population mean or the population parameter using the descriptive statistics, but that will come a little bit later. So when we're using descriptive statistics, we're really trying to describe the distribution. So if you notice back up here, it's a set of techniques used to describe the distribution of a variable. So the distribution shows what values are possible and how frequently those values occur. So if you're thinking about you roll a die, you roll it, you can get a 1, a 2, a 3, a 4, a 5, or a 6. And if it's fair, we assume that each one of those outcomes occurs with probability 1/6. So we would say you'd get a 1 1/6 of the time, a 2 1/6 of the time, a 3 1/6 of the time, and so on. So that's the distribution of a variable. What values are possible and how frequently those values occur in the population. And if you know the distribution, you know everything there is to know about that variable. So you know its mean, you know its median, you know its variance, the standard deviation, you know everything you need to know if you know the distribution. And the reason we care about the distribution is in this course, the distribution is linked to risk. So if we think about a particular stock, we have the average of that's the average return, the standard deviation of returns. Again, we're going to talk about all this stuff in more detail later. You know everything you need to know if you know the underlying distribution. But in practice, we never actually know the distribution. All we can do is describe the distribution using what we observe in the sample. But if you know the distribution, you know everything. But I can't think of hardly any scenarios where we actually know the distribution for anything. We just know what we observe and we make inference about the population using what we observe in the samples. Right? So all we're doing with our descriptive statistics is describing the distribution in the sample. We don't know the underlying distribution. We're just trying to describe that distribution using a set of sample statistics. If we want to generalize results from our sample to the population, a lot of assumptions need to be met. We need a large random samples. We need things that really go beyond the scope of this class, but the main one is we need our sample to actually reflect that underlying the population that we're trying to make inference about. A couple ways we will describe variables. We're going to cover all this stuff in Excel. Measures of location, mean, median, the quantiles, min, max. So that's going to tell us where the distribution is located. We also want to think about how the distribution is, the shape of the distribution, or how spread out the variables, the values are. So variance, standard deviation, range, interquartile range. So the range is just the max minus the min. So this is the difference between the maximum value and the minimum value. And the interquartile range, you may see it abbreviated as IQR, is the difference between the third quartile and the first quartile. You know, the second quartile is the median. So it's already summarized here, but you'll see Q3 minus Q1. That's the interquartile range. Some other things we'll use to describe the distribution, not in as much detail, but we do use these occasionally. Skewness, this is going to tell us how the shape of or the symmetry of the distribution. So if you think about, if you've seen a normal distribution, we'll see this later, it's perfectly symmetric. So it has skewness of 0. Kurtosis, it tells us how much of the distribution is in the tails, so how likely are extreme values. If we're working with two variables, we can think about the covariance and correlation. So when we're making scatter plots later, that's when we're working with two variables at one time. So we want to see how two variables relate to each other. So we can use covariance and correlation to do that. That's also going to be very closely related to regression, where we actually estimate relationships between two variables and form a model that we can actually use to make some inference or predictions using the observed values. And we can also describe variables visually, so we can make histograms and bar charts, line plots, scatter plots. There are a number of these things that we can do, but these are the three that we'll use most of the time in this class. So there are a couple of different ways we think about data, a couple of different data types. There's cross-sectional data. So this is when we observe many subjects at the same point in time. So if I go around the class and I ask everyone, how old are you? That's a cross-section, because I'm observing every person in the sample exactly one time, and it's at the same point in time. So how old are you right now? And if I write all that down, I have a cross-section. If I ask everyone for the current GPA, that's a cross-section. So the sample would be the students in the class, and then each observation would be the GPA for a particular student. So that would be a cross-section. We're going to work with a lot of time series data in this class. We're going to work with cross-sectional data as well, but a lot of what we're going to do will focus on time series data. And this is when we observe data for a particular entity over multiple time periods. So what we're going to think about mostly is stock price. So if we think about stock price and we have it recorded monthly, so what is the price on the last day of the month for a particular stock? So let's say we look at Bitcoin, and we look at the price on the last day of the month for the last 5 years. That's a time series, because we have one entity, Bitcoin, and we're looking at the price over time. So that would be a time series. A couple things you have to be careful about with time series is you have to make sure you're working with stationary data, because non-stationary data looks a little bit different, and we can't apply the typical statistics from it to non-stationary data. So if it's non-stationary, it means it does not have a mean. It's a trend that's trending up, it's trending down, or just but there's no mean that the series fluctuates around. So I'll show you a picture of this in just a second. And again, we can't apply conventional statistics because they have a conditional mean but not an overall mean. Because if you take a different chunk of the window, the mean is going to be different. A variable is stationary if it fluctuates around some average value or stays within a certain range. So if you have a series that sometimes it goes up, sometimes it goes down, but the average, but it fluctuates around some fixed average, we would say that is stationary. And that's what we have to transform the data to make it stationary, but it's a fairly simple process. So here's a picture of two things that are one that's stationary and one that's non-stationary on the left and stationary on the right. So if you look at the housing price index, so what this does, it measures average price changes. So it's normalized so that the base year is 2000. So what we're going to do is compare everything to year 2000 prices. So in 2000, we're going to normalize this to 100. If you go up here to 200, so let's come up here and go all the way over to the right and down. So it looks like by 2022, housing prices were about double what they were in 2000. So it took about 22 years for home prices to double in Bowling Green. Again, this is using the Bowling Green Metropolitan Statistics, the Bowling Green MSA. So this is actually Warren County and a few of the surrounding counties. So this would be the average there. But that's how we read this index. So if we look here, housing prices are going up. So this is around the financial crisis right here, 2008, 2009. There's a little bit of a dip in the housing prices, and then some seasonal fluctuation here, but on average, prices are going up. So we saw a really, really big spike in housing prices during COVID, and this is where interest rates went to zero. A lot of stimulus money floating around. The housing market really took off, and it did this just about everywhere in the U.S. So Bowling Green was not unique here. And then prices started to level off a little bit. But notice how this series is basically trending up. And if you think about forecasting this way into the future, which forecasting is really hard to do, we would assume prices tend to continue increasing. Now this plot on the right, so this on the left would be non-stationary. This plot on the right is the change in the housing price index. So this is using the difference or the percent change 1 year ago. So notice we lose 2000 because that's our base year. But this says housing prices in 2001 were just under 5% higher than they were in 2000. So this is the percent change from 1 year ago. So if you look at this right here, so right here we're at about 7.5%. So in 2005, prices were about 7.5% higher than they were in 2004. And notice how this is not trending up or down. It kind of fluctuates around some value. Again, sometimes it goes down, sometimes it goes up. But if you look at this, it's hovering around a mean. We kind of have to ignore this big bump during COVID right here. But notice we have this big run up and then this drop. And then things started to level off a little bit. So this is pretty wild right here, where we were seeing almost a 20% increase in housing prices in a given year. So the right plot, again, 5% may not be the right number, but what you can see is it is hovering around some, or revolving around some fixed value. So we have to get the data in this form before we can work with it. We can't really work with this type of data. We will a little bit, but we're mostly going to be working with these stationary series. So we talked about the different types of data. We also want to think about different types of variables. So variables can be categorical, which is when we assign an observation to a particular category. So we've assigned male, female. So in 99% of survey data that you work with, government data, you'll see male, female. So you have to be in one category or the other category in the survey. You're not allowed to check more than one box. Now there are surveys that allow for male, female, other, male, female, prefer not to say. There are a lot of different categories that you could have, but the main point with categorical data is you can only check one box. So econ major, finance major, accounting major, if you're a double major, we would have to create a different box for that major because we can't have more than one box checked at any given time. And we can describe categorical variables with words. So we can actually have text that describes a variable, and then I'll show you later how we convert that to something that's numeric for us to work with. So we can apply the statistics to that variable. Quantitative variables are represented with numbers. So it's important to note that sometimes you have things that are measured with numbers that are not quantitative. But if it's quantitative, it will be measured with a number. For example, the zip code is a number. So I live in 42104. That's the zip code I live in. I can't take the average of zip codes. It doesn't make any sense. So not all numbers are quantitative, but if it's quantitative, it will be measured with a number. Sometimes categorical variables are things that are categorical are still represented by numbers. So age, GPA, income, these are all things that are quantitative. It's a number that we can use to describe the value of something for a particular observation. They can be discrete or continuous. So a discrete variable is a variable that can only take on specific values. So if I ask you how many children you have, 0, 1, 2, 3, 4, 5, 6, you can't have 1.5. We're not going to treat step kids or something as halves. You have 1, 2, 3, 4, 5. The number of bedrooms in a home, 1, 2, 3, 4, 5. The number of bathrooms, it's a number. So we have, sometimes you'll see 2.5 baths. What that really means, it has 2 full bathrooms and 1 half bathroom. We don't have 2.5 bathrooms. So the number of full bathrooms would be a variable. The number of half bathrooms would be another variable. So you can't have 2.5 bathrooms. Continuous variables can take on any value. They can be measured as precisely as we want to measure them. So height can be measured down to the fraction of an inch, weight to the fraction of a pound. Some things that look like they might be discrete because you think they can only take on certain values, we still treat those as continuous. So if we think about the price of a house, we treat that as a continuous variable, even though when you're transacting a home, you're working, you have a house under contract. Rarely are you going to offer $350,000.75 for the house. It'll be some round number, but we still treat it as continuous, as if it could take on any particular value. And we need to know what type of data we're working with, because the techniques that we use are determined by the data that we have. If you have discrete type variables, we apply certain methods. If we have continuous variables, we apply certain methods. If we have categorical variables, we apply certain methods. And what you'll see later is we're going to take these categorical variables right here and we're going to convert them to something that is what we call a binary variable or a dummy variable, that we represent those words with zeros and ones. But the technique depends on the type of data that we have. And just to show you quickly, this is a sample of housing data that we're going to work with a little bit later. And you can see the different variable types. So this is actually not a variable. This is just something that just tells me which observation I'm working with. This sold month, so that's the month that the property sold. Yet all of these, this is a sample of sold properties from Warren County, I think from 2024. So this is the month. So notice we have January, February. But we're representing January with a 1, February with a 2, and so on. This is the categorical variable right here, because it describes the area that the property was located in. So we can't be in more than one category. You can't be in Smiths Grove and Bowling Green downtown. You have to choose one. So this is categorical. This is also categorical because it's a number, but it describes where the home was located, and you can only be in one zip code. Days on market, we would treat that as continuous, even though we're going to measure this in increments of 1 day. We would treat that as continuous. The number of bedrooms, full baths, partial baths, those are all quantitative, but we're going to treat those as discrete. There are times when we will treat those as continuous, but a lot of times it's better to model. If you're trying to estimate sales price, to treat those discretely. We're going to treat square footage as continuous, even though we're not looking at fractions of feet. We're still going to treat that as continuous. List price is quantitative, continuous. Sold price, quantitative, continuous. So we can take the average. We can take the average of all of these variables, and the number that we get would make sense. I'm sorry, even this one too. So we could take the average of these variables, then the number would be meaningful. If we take the average of zip code, we're going to get a number, but that number is not going to mean anything. We can't take the average of area. Now you can think about the mode here. What's the most common area? But the typical standard deviation, min, max doesn't really make sense when we're looking at a variable like that. Okay. So those are the different types of variables. And this is the same data just in the slide. It's just a little bit easier to see if I pulled that sheet up. And one of the last things we need to think about, and it's very important, even though in this class I'm going to give you most of the data that you need, you're not going to be taking your own samples and constructing your own data sets. But we need to think about choosing the right sample. And how do we know if the sample that we have is good? And when I say good, I mean representative of the population. Or when do we need to be a little concerned that maybe we apply all the fancy statistical techniques, but it doesn't really matter because the sample doesn't reflect the population of interest. So if we're going to describe a variable in the sample with the goal of making inference about the population, we have to make sure a couple things hold. Again, the sample is just the part of the data that we actually observe, the part of the population that we actually observe. We need them to be representative of the population. So we need to have a clear understanding of the population we're trying to study. So you need to have a very clear idea. This is what I'm interested in making inference about. And then we need to choose the samples carefully to make sure we understand the limitations of the way we're sampling. So in a perfect world, you would have access to the entire population. That doesn't happen in practice. So if we're interested in the average, let's say the average household income for Western students, and for students at WKU, that number does exist. We will never get our hands on that number. So if you take a random sample, or if you, let's just say you sample your friends and you ask all of your friends, well, how much money, what is your household income? That's not going to be a great sampling strategy because if your friends have, you might gravitate towards friends who are similar to you, who may have similar backgrounds. That's not going to be representative of the population unless you just happen to be average. Let's say we want to estimate the average height of a Western student, but we only sample football players or basketball players. That's not a great sampling strategy. What we want when we sample is for every observation to be equally likely to be selected. So if I want to know the average income, average household income for Western students, I would like to have a large random sample of Western students where I'm just as likely to get the richest household as I am the poorest household. I'm just as likely to get households that are white and households that are black, households that are whose parents are educated, households whose parents do not have higher education. Everybody needs to be equally likely to be selected. And if that's true, and if our sample is large, and if it's random, we can have some confidence that our sample actually reflects the population of interest. It's possible to do everything right and still get a poor sample, but if your sample is large and random, that gives you your best chance of having a sample that matches the underlying population. Then a couple more examples of poor sampling. Athletes to get the average weight of all students. 1 week of stock returns to measure stock performance. That's poor sampling. Another thing we have to make sure we do when we're sampling is thinking about the level that we're trying to make inference about. So let's say you're interested in housing markets. So if we look at the housing price index over the last almost 25 years, things have evolved differently in Los Angeles and Bowling Green and the United States on average. So if you look at the U.S. average since 2000, values have appreciated more than they have in Bowling Green, but less than they did in Los Angeles. If you're looking around this big housing boom and bust right here, Los Angeles had a really big boom and a really big bust. The U.S. also had a boom and a bust, but not as severe as Los Angeles, and home values were fairly steady in Warren County. We saw an increase, but not nearly as large of a decrease. So they started to drop a little bit out here, but a little bit later than they dropped nationally, or than they dropped in the U.S. or even in Los Angeles. So let's say you want to know, someone asks you, well, how strong is the housing market, and you just use national estimates, but you're making inference about Warren County, you could be very, very wrong. Or maybe you have information from Warren County and you think, oh, well, if it's strong here, it must be strong everywhere. Well, that's not necessarily the case, because we can see right here, values were still increasing a little bit when they were decreasing very quickly nationally and in some of the larger cities. So you want to make sure your sample is large, it's random, and that it actually reflects the population that you are trying to make inference about. So in the next video, I'll go through some things in Excel showing you how to estimate these descriptive statistics a couple different ways. So we'll talk about all the basic descriptive statistics and how to make pivot tables and bar charts and histograms, scatter plots, and all the things you'll be responsible for knowing moving forward.